So today we have the final practical exercise and the course project. I think is the task 6, and for the final subtasks, and for the before the lab, and I would like to mention about we will need some template or some programs, and you can find it on others, and you will see this is the uh, 13 topic, and here has 5 program, and each of them you need it, and however I find it's hard. I don't know where to download it, and you can just I would say you can just copy it, and you will here, and you can open a new script and face it and save it. Use the same name as it mentioned here. It will use this name and PD6 and the culture amplitude modulation 16. Use this name. So for the other programs, there will be the same things, and this is for the AVGN function, and or you can load it the packages, or you can just also you can choose to download it or just save it, and so these 3 programs, they are working for our sixth the practical exercise, and we have some encoding and decoding functions for the course project, and you also have to save them and use there it mentioned the name, and for the decoding functions also can save it as it use it mentioned name. So that's all what I would like to mention about the course information, practical information. And let's move to the lab 6. And for the final practical exercise, we have to find out the noise immunity of the culture rate amplitude modulation 16. And we similar to the previously practical exercise, we have to find get our received signal constellation plots for the different signal to noise ratio, and you will see here we have some recommended signal noise ratio range from the 5 decimal to the 10 dB, and you will evaluate the bare values for different signal noise ratio values, and you will determine the number of the errors for you will count the errors and for each signal noise value, and estimate its error probability, and make your conclusion on the noise immunity. So firstly, similar to previous case, we have to generate our binary data, and for this case, we will not specify some like 10 symbols or just 10 or some small small range binary data, and we will randomly generate 1 minute binary data use functions, and you will see for the chord rate amplitude modulation tab, and for the one symbol will carry the 4 binary bits. So we have to convert the single like row vector and convert it to some matrix, and the matrix dimension will be defined by your how many data you will transmit, and you will according to the 4 bits of the 4 bits of the per symbol. So we can know that the row, the data matrix will be the row is determined is the 4, and for the column that will be the total number of the binary data divided by 4. So that is idea, and we can do it's already did it for here, and you will see here some variables already given in here. First is the how many numbers we have to transmit, and we generate the integer numbers in range of the 1 or 2, and we subtract the 1 so we can get our desired 0 or 1, and we have to specify some single to noise ratio. And let me see which is range with the maximum range is the value is the 10, and here we have to do so. Firstly, we have to do some format the binary data, and which consists of the 4 bits per symbol, as I was just mentioned about that. So we will use some reshape function, and we open the command, and let's do it. So the reshape the dimension will be the 4 4 is our row, and n divided by 4 is our columns. So the binary data is here, and for the row is 4, and for the column is n divided by 4. So finish the first step. We do we format the data, and now we have to convert the each like how to say each column. This is one 4 bits, and which is 4 bits. We have to convert it from the binary to decimal, and we will use some multiplication. And so if we have 4 bits, so the maximum the decimal value will be the power of the 4. So the 2 power of 4. So the maximum decimal value will be the 16. And our binary data is started from the 4000. So it will start from the 0, and its range is 0 to the 50, 15, and we will use this. We will use the power and to multiply them with our binary data matrix and convert them to the decimal format. And how can we generate this one? And we will use some here already mentioned about we will, so we can do it, and we will use some index here, like 3 to -1. Step is the -1, and the last one is the 0. And we think about that this is our power, and the 2 power of 3 to power of 2 or power 0, and we can use the dot like this one, and will be just copy it. So, and we can generate this in the index with for the first bit, second, and third, and the fourth bit. And we multiplied with the binary data, So the code will be, I just copy here, and we open the here we open the convert command here, and use this this index and divide by the our binary data. So we finished the second step, and the result will so for the decimal result, which encoded, we consider it as some index because we will find the our binary data which will match with this cultural and amplitude multiplication 16 with its consideration, and it's already given in the MATLAB, and you will see here this is 16 columns, and no, this is single column, and we can see here it will arranged by some order. You will see the real part and the image part, the -1, which is represented as here, -1 and -1. So the index is 0, and for the next one, -1 and -3, they will be the index over the 1. So it's followed by order 0, 1, and go further to the 15. So totally we have 16 corresponding point corridors, and we will use the analytic method to modulate our data, followed by this consideration, and now we know the modulate index is 0 to 15, and our binary data also is the 0 to 15. So each of them, this is the index. Each of them will find the corresponding the point coordinates. For example, we have the 0 here, then your the corresponding the point is this one, -1, and if we have like 4, and the corresponding with is the -3 and the -1, which is the 4 here. The and the real part is the -3, and the image part is -1. So this is idea, and we have to use the index here. However, each symbol we have to increase by 1 because for the binary data, and here the map, and it will start from 0 to the 15, and for the MATLAB index start from the 1. So you will see here when we use the map function, and we have to +1. After that, we can do some use the AWGN function to add some noise. So, and we can plot such a graphic. So let's do it. And here is already added, and for the it's add 1, which is a map character index from the 1 to the 16, and we have to use the aviation function to add some noise. So this will be the modulated data. And we give the signal to noise ratio value we already specified here. And after that, we can plot it. So it's mentioned about here. And the blue dots is noise signal, and the red cross is ideal signal. So we need to plot both of them. First one is the noise signal. And we will give some blue dots. And for the ideal signal, which is this one, right? And we give it as a red cross. And we give some X exercise and Y exercise some elimination. X, yeah. And also will be -4, 4. And we give it labor. So X labor will be the real part. Y label will be some image part. And we will give the actual sum square, which is quite makes it looks like this. Use some square to eliminate the all modulated the noise signal and the down signal in this square. Just and so that's right. Yes, you will see here, and the all binary data will followed by the specific the position of the ideal signal, and you will see all of them close to them. And if you zoom it, and you will see here, this is ideal signal, and some of the noise, some of the noise signal which is quite far to the ideal signal, and its main depends on your specific single noise ratio. And now let's to increase it like 30. So how it will look like. Yes, and now you will see, well, all of them, they are quite stay together and quite close to the ideal the signal. And if you increase it again, So you will see the noise signal there looks like hidden inside of the ideal signal. And when you zoom it, so you will find there here, and the distance is quite shorter, right? So the quite shorter, so we'll have the lower mistake. And for here, I would like to mention about that dimension of the here for the this is for the consideration. This is a single column vector you will see here. So this is single column vector, and for the binary data, and this is for the this is reshaped binary data. So this is a decimal binary data, and you will see here is a single row vector, and it's range from the 0 to the 15. And what else? And for the modulated symbol you will see here, and each of them will find the matched corresponding the position, right? So this is idea, and this is also the single column, and similar to the, the ideal signal. So when we finish the modulated part, next we will use some demodulation part. So we will open another template, which is the modulated data, and you will see for the main program, and after that we will perform the demodulation, and we have to find the close the ideal signal from the consolidation, and we still have to convert the decimal symbols to the binary code words, and we will load this script, and after that we will calculate the how many errors happen, and calculate the errors ratio. So we just load this data, this file, and we will do some modifies in the demodulation secret. This is a sub secret, and let's come back to the guidelines. And for the culture rate amplitude modulation 16 signal detection, and we will use some. So the basic idea, we have to calculate the difference between the received symbol and each ideal symbol, and you will see the red cross. This is the ideal signal. So we calculate all. So if the received signal, I don't know, it will stay at here, and it will calculate all of them the distance. So if the minimum distance, which one is it's a minimum distance? So if the if calculate minimum distance is the minimum value is here, so it will belongs to the here. So and we can finish the demodulation. So this is a basic idea. However, we will to use some matrix subtraction, and we have to make sure that all the dimensions they will be same. And the the both vectors, we have to use some remap function. So what is the remap function? Suppose we have, let's see, we have the x will be the 1 joule. If you use the remap, with x, so we have to specify some dimension. I hope to at 1, and it only has a 1 is for row, and we have, if I want to have 2, and it will have the 2 row, and for here I don't just want, and it will have the single 2 columns, and if I have the, I only wanted the 2 rows and the 1 single column, and here, and you will see here. So this is idea. We just repeat of the signal, and to match the dimensions, which with our received received signal, and with the ideal symbols. And let's move to here, the separate script, and we here so the received symbols, we have to create a matrix with the dimension with the and divide by 4 with the 16, and now the whole matrix will be the which we have to remap here. This is our modulated data, and which is a noise signal. We know its dimension is 25,000. 50,000, and we will reshape it as some we don't change its the row dimension. We just want to hope it matched with our here with the column dimension. We are hoping as the 16. So it will be the n divided by 4. This will be the 250,000 for row, and the 16 will be the columns. So this here, and we just copy it, and for the noise signal, and for the row is 1 because it's already this value. We don't change it, and we only change it as the 16 to remap it as the 16 columns, because in here we only have the dimension is 1. So after we use the remap function, so it will get the 16 same columns with dimension here. And so let me check it. What will, and this is the noise signal, and this is noise signal, and this is our remapped signal, and you will see here all of them, they are same, right? This is the same column, and this is the second column. This is the third column and all of them up to the 60 column. So we don't do any change here. We just copy it up to the 16 columns. After that, we will compare it with our ideal signal. We know that ideal signal is the red cross is here, and it only the red cross at 16. It only has 16. So we must to change the same dimension with the our noise signal here. So let's do it here, and we use the remap function. Remap function is here, and for the map, and for the here, and we have to do some. First, we have to do some reshape it, and you will see here is this is a single column. We hope to reshape it as the single row. However, it will change the here. It will change the opposite the value. So we will use some dot transform prime. Then nothing will be changed. And so this is basic idea. Dot. Right. So this will be the single row, and for the so 16 it is a single row and 16 columns. So the columns here we don't have to change the anymore, and the only things we have to pay the and divide by 4 dimensions the row, and their dimensions will be same, and we use the yielding distance to do it, to calculate the to find out the minimal distance, and we only need the absolute value. So it would be the noise signal to minus subtraction of the signal. And we have to use some, the next step, we will find out the minimal distance in each row and determine the column of the number of this minimal. And we will use some function, use the minimal function, and it will be the distance. And with the symbol here, I think here already. Yes, and we use some, so for the minimal distance matched to the column number in this measure. Minimal index can found user. You will use the main function, and with the 2 output arguments, and we have to specify the minimal is searched in the second matrix dimension. So we just copy this one, and these minimal values are decimal, and we have to convert it come back to the binary data. And now we will use this one. And convert, use the decimal to the binary to convert the data. And here you remember we add 1 in here, and after the demodulation we have to -1, right? And we have 4 bits right here. After that we will compare with 1 text. So finally we have to convert all the here is broken the matrix into the single column, and we have to convert to those. So we use the data with the symbol and converted the row. So this is for the binary. So this part will finish for the modulation part, and let's run it again. And you will see here we have to compare come back to here. So the distance matrix, and this is the distance before them, and each of them there we have to find out the minimum value and the distance, and with this is we have minimum each row and determine the column number of this minimum. And for the here it's already decide which the value of it, and these are all decimal value. And after that we have to convert to the decimal to binary, and you will see here binary data. And so this is already after the decimal convert to binary, and we will do some compare with one text chapter and the output of the string, and we perform the local comparison to obtain the numeral values. So we get the numeral values, and we convert when the matrix we convert the matrix to the single column, and it will be the same with our transmitted data. Here, this is also the binary transmitted binary data is also the single single row. And after that, we can count the number of the errors, and we will comparing the vectors in the binary data and binary demodulation data. So we just the sum is how many of the different with the binary demodulated data being equal to the binary data. So it will be the number of the errors. And we calculate the number of errors ratio, which is the error divided by so total transmit number is the 1 milli. And let's do it. And you will see here the number of error is the 0, so the number of the error ratio is also the 0. And in our case, our signal to noise ratio is the 50. And we have to use some recommend signal to noise ratio from the 5 to 10. Let's do it with the 10. And firstly, we check the plots, and it looks like quite clear, and the distance also very obviously. I believe maybe there are some little mistake. So only one mistake. We transmit the 1 minute data. Only one mistake happens, and let's change the value of the 9. So for the 9, we have 25 errors, and we can see here. So what else for the 8 and 100, and if we transmit for the 5 and the 4,500 of, and let's see plot. So you will see plot there is the modulated data. It looks the modulated data is not very clear after added lots of noise, and so in your case you will compare all the different signal noise ratio and make your own conclusion on the noise immunity of the culture rate amplitude 16 modulation format. And don't forget your plot and your plot or your error values and the bare values and your for source code. So that's all for our last practical exercise. And let's take I don't know, for the 10 minutes break. We can come back at the 10:50, and we will finish our last cross project task. And thank you. I will stop sharing.